Good morning and welcome back to Laplace transform of Heaviside step and Dirac delta functions. In this session we are going to discuss Laplace transform of Heaviside unit step function, second shifting theorem, Laplace transform Dirac delta function, inverse of functions involving e raised to minus as, solution of ODE involving Heaviside unit step function or Dirac delta functions. First of all, we are going to develop a formula to find Laplace transform of unit step function. We have to prove that Laplace transform u of t minus a is equal to e raised to minus as by s. For that, I start from the basic definition of Laplace transform. L of f of t is equal to integral 0 to infinity this f of t e raised to minus st dt. Here the function f of t is u of t minus a. So I substitute u of t minus a in the place of f of t. So L of u of t minus a is equal to integral 0 to infinity u of t minus a into e raised to minus st. But this u of t minus a has only two values 0 and 1. When it takes 0 when t is less than a and gives value 1 when t greater than a. So when we substitute the value of u of t minus a, this integral limit changes to a to infinity, and u of t minus a becomes 1 when t greater than a. So this u of t minus a becomes 1, then kernel e raised to minus st dt. The remaining is just integration of e raised to minus st with respect to t. So integral e raised to minus st is e raised to minus st by minus s. Then I put limit from a to infinity. L of u of t minus a equal to e raised to minus as by s. That means Laplace transform of unit step function equal to e raised to minus as by s. Now we are going to discuss one of the most important theorem in this area, that is second shifting theorem. The second shifting theorem says that if the function f of t is shifted by a units, then in its transform affected in multiplication by e raised to minus as to Laplace transform the original function f of t. Or if f of t has the Laplace transform f bar of s, then Laplace transform f of t minus a into u of t minus a equal to e raised to minus as into L of f of t or f bar of s. Intuitively speaking, shifting in time domain leads to multiplication by e raised to minus as in the transform domain. That is the meaning of shifting theorem. To prove this, I start with the definition L of f of t equal to integral 0 to infinity f of t e raised to minus st dt. And therefore, L of f of t minus a into u of t minus a equal to integral 0 to infinity the function f of t minus a into u of t minus a into kernel e raised to minus st dt. But u of t minus a takes 1 when t greater than a. So the limit changes to integral a to infinity f of t minus a into 1 e raised to minus st or f of t a into e raised to minus st dt. Then I put a transformation t minus a is equal to tau, and therefore t is equal to t plus a, tau plus a. Then we take differential on both sides. I got dt is equal to d tau, and when we put the lower limit a for t, tau is equal to a minus a 0, and I put upper limit infinity to this t, infinity minus a is again infinity, so upper limit of tau is infinity again. And I put in this limit and transformation integral 0 to infinity f of tau e raised to minus s into a plus tau d tau. Here the integration variable is tau. I can take e raised to minus as outside. So e raised to minus as into integral 0 to infinity f of tau e raised to minus s tau d tau. Using a reverse definition, integral of a function after multiply by e raised to minus s tau resulted in Laplace transform of the function f, that is L of f, or Laplace transform of shifting leads to e raised to minus as into Laplace transform of original function f of t. So the proof is over. Now we are going to define L inverse of a function with e raised to minus as. From the second shifting theorem, we know L of f of t minus a into u of t minus a equal to e raised to minus as into Laplace transform of f or f bar of s. Then I take this L into the right side. I got L inverse. L inverse of this expression e raised to minus a into f bar of s equal to f of t minus a into u of t minus a. Or intuitively we can think like this: effect of e raised to minus as in the inverse is u of t minus a. Now hide this portion e raised to minus as. Remaining is L inverse of f bar of s. Then replace that t by t minus a, that is f of t minus a. We will see this in the next problem. Find the Laplace transform of f of t is equal to 0 when 0 less than or equal to t less than or equal to 3, t when t greater than or equal to 3. We will solve this problem by diffusing this f of t into a single line function using unit step function, then apply the results of Laplace transform of unit step function and second shifting theorem. So the first step is rewrite this function as a single line function using this unit step function. So start with the base definition 0 plus difference t minus 0 into u of t minus 3. In essence, f of t is now t into u of t minus 3. Now apply Laplace transform on both sides. L of f of t is equal to L of t into u of t minus 3. Now look, here we have t minus 3. So we have to rearrange this t to get a t minus 3 term here. So t can be rearranged as t minus 3 plus 3. When we simplify this, we get t back. So L of t minus 3 plus 3. Then we distribute this and apply Laplace transform. So L of t minus 3 into u of t minus 3 plus 3 into L of u of t minus 3. Apply shifting theorem here, second shifting theorem here, and evaluate Laplace transform unit step function. That is equal to e raised to minus 3s into L of t plus 3 into L of u of t minus 3 is e raised to minus 3s by s. Laplace transform of t is 1 by s square. So e raised to minus 3s into 1 by s square, or e raised to minus 3s by s square plus 3 into e raised to minus 3s by s. Taking LCM and e raised to minus 3s outside, e raised to minus 3s by s square equal to into 1 plus 3s. So Laplace transform our original function f of t is equal to e raised to minus 3s by s square into 1 plus 3s. That's all. Now we move on to next problem. This again a multi-valued function f of t. It is equal to t when 0 less than or equal to t less than or equal to 2, 0 less when t greater than or equal to 2. Combine this function using unit step function, then apply Laplace transform with the help of second shifting theorem. So f of t is equal to t plus 0 minus t into u of t minus 2, or it is t plus minus t into u of t minus 2, or t minus t into u of t minus 2. Now apply Laplace transform on both sides. So L of f of t is equal to L of t minus t into u of t minus 2. That is equal to L of t minus L of t into u of t minus 2. Okay, now I rewrite t in terms of t minus 2 in this expression only. So t can be written as t minus 2 plus 2. I write in terms of t minus 2 because I have u of t minus 2 associated with this t. T minus 2 plus 2 into u of t minus 2. L of t minus L of t minus 2 into u of t minus 2 plus 2 into L of u of t minus 2. Apply shifting theorem here and use definition of Laplace transform unit step function. L of t is equal to 1 by s square minus L of t minus 2 into u of t minus 2. You can think like this. Effect of u of t minus 2 is e raised to 2s minus 2s, e raised to minus 2s. Then remaining term is you avoid this u of t minus 2 and 2 L of t plus 2 into e raised to minus 2s by s. L of t is again 1 by s square. So e raised to minus 2s into 1 by s square. So we got the solution 1 by s square minus e raised to minus 2s by s square plus 2 into e raised to minus 2s by s. Now on simplification we got 1 by s square minus e raised to minus 2s by s square into 1 minus 2s. Okay, we move on to next problem. Find the Laplace transform of sin t into u of t minus pi. It is more straightforward. We have to replace t by t minus pi plus pi. That's all. Sin t is equal to sin of t minus pi plus pi. We can use sin a plus b result. Sin a cos b plus cos a sin b. But sin pi is equal to 0, cos pi is equal to minus 1. So this sin t becomes minus of sin t minus pi. That is equal to minus sin of t minus pi. Now we use this result, second shifting theorem. L of f of t minus a into u of t minus a is equal to e raised to minus as into f bar of s. Therefore, our problem L of sin t into u of t minus pi becomes minus into L of sin t minus pi into u of t minus pi. Apply second shifting theorem. Effect of u of t minus pi is e raised to minus pi s. Now hide this term and this pi. Remaining is L of sin t with a negative. L of sin t is 1 by s square plus 1. 1 by s square plus 1. This negative is here. So the answer to this problem, L of sin t into u of t minus pi is equal to minus e raised to minus pi by s square plus 1. Okay. Now we are going to find inverse Laplace transform involving e raised to minus as term. Okay, find the inverse Laplace transform of s into e raised to minus 3s by s square minus omega square. First step is using this result. L inverse of f bar of s into e raised to minus a is equal to L inverse of f bar of s with t tends to t minus a into u of t minus a. We can think of like this. Effect of e raised to minus as in this transform is u of t minus a. Then hide this term. Remaining term is L inverse of f bar of s. Write that L inverse of f bar of s. And finally replace this t by t minus a. So we start with our problem. L inverse of s into e raised to minus 3s by s square minus omega square, that is equal to effect of e raised to minus 3s in this function is u of t minus 3 in inverse u of t minus 3. Hide this term. Remaining term is L inverse s by s square minus omega square. Then put t to t minus 3 after evaluating this inverse. This is s by s square minus omega square. Since it is negative in denominator, it is cos h. So cos h omega t. Then replace t by t minus 3 into u of t minus 3. Now the last step, replace t by t minus 3. Cos h omega into t minus 3 into u of t minus 3. So we got L inverse of s into e raised to minus 3s by s square minus omega square equal to cos h omega into t minus 3 into u of t minus 3. Next problem. Find L inverse of 3s plus 1 into e raised to minus 3s by s square into s square plus 4. As in the previous case, I take the effect of e raised to minus 3s, that is captured in u of t minus 3. And the remaining term is L inverse of 3s plus 1 by s square into s square plus 4 with t tends to t minus 3. That's all. Now we have to find the L inverse of this term and finally change t to t minus 3. So I consider this expression in the bracket and apply some tricky approach. I take 3s plus 1 outside, 3s plus 1 into 1 by s square into s square plus 4. Then this term can be simplified like this, minus of 1 divided by difference of these factors. So difference of these factors is minus 4. Minus 1 by minus 4, 1 by 4 into 1 by first factor minus 1 by second factor. Then multiply this 3s plus 1 into this bracket. So 1 by 4 into 3s plus 1 by s square minus 3s plus 1 by s square plus 4. Term by term division. 1 by 4 into 3 by s plus 1 by s square minus 3s by s square plus 4 minus here 1 by s square plus 4. Now L inverse on both sides. L inverse of 3s plus 1 by s square into s square plus 4 equal to 1 by 4 into 3 plus t minus 3 cos 2t minus half sin 2t. We take individual L inverses. 3 is a constant. L inverse of 1 by s is 1. L inverse of 1 by s square is equal to t raised to this n minus 1, that is t raised to 1 by 1 factorial, that is t, minus 3 into s by s square plus 4. Inverse of s square by s by s square plus 4 is cos 2t, minus L inverse of 1 by s square plus a square is 1 by a sin at. Here a is 2, so 1 by 2 sin 2t. Now we finally replace this t by t plus 3 to get the final solution. That is, replace t by t minus 3. 3 plus t minus 3 minus 3 into cos 2 into t minus 3 minus half into 2 into t minus 3. Definitely u of t minus 3 here. So final answer is like this. We can simplify this expression. 3 minus 3 gets 0. So t from here. Minus 3 into cos 2t minus 3 minus half into sin 2 into t minus 3 u of t minus 3. So nothing more. We calculate the Laplace transform the term except e raised to minus 3s, then we replace t by t minus 3. That's all. The Laplace transform Dirac delta function. Next important function is Dirac delta function. Laplace transform Dirac delta function is defined like this. L of delta of t minus a is equal to e raised to minus as. So if Dirac delta function is argument, Laplace transform is simply e raised to minus as. In the case of unit step function, there is e raised to minus as by s. Here there is no division by s. Now we are going to connect Laplace transform Dirac delta function and Laplace transform unit step function. The Laplace transform Dirac delta function is equal to s into Laplace transform of unit step function. That is a relationship. So when we take Laplace transform unit step function about the threshold a, when we multiply that output by s, we got Laplace transform Dirac delta function with the threshold a. So we use L to the right side. So we got L inverse of e raised to minus a is equal to delta of t minus a. That is another result. L inverse of e raised to minus a is equal to delta of t minus a. If there is only an exponential function in our transform domain, then its inverse gives Dirac delta function. That is another observation. So I will solve one ODE using our Dirac delta function and unit step function. In this problem, we consider Dirac delta function R of t. The problem is find the response of the hammer blow of a mass spring system modeled by y double dash plus 3y dash plus 2y is equal to delta of t minus 1 with initial conditions y of 0 and y dash of 0 equal to 0. So the solution procedure is same as in the previous session. We apply Laplace transform on both sides, then substitute the initial values, solve for y bar of s, finally take L inverse. That's all. So the only change in the right side, instead of t square and e raised to function like that, we have delta of t minus 1 in the R of t section. That is the only difference. Okay, we start the solution. I write the problem y double dash plus 3y dash plus 2y is equal to delta of t minus 1. Now apply Laplace transform on both sides. So Laplace transform y double dash plus 3 into Laplace transform y dash plus 2 into Laplace transform y is equal to Laplace transform delta of t minus 1. We evaluate this. Laplace transform y double dash. We have that result s square into y bar of s minus decrease the power of s by 1, s raised to 1 into y of 0 minus decrease again power of s raised to 0 into y dash of 0. This term, 3 terms corresponds to Laplace transform of y double dash. We have that result plus 3 into, I put a bracket here, y dash 1 differential, so s into y bar of s minus y of 0 plus 2 into y bar of s equal to, we know Laplace transform Dirac delta function is e raised to minus as. Here a is 1, so e raised to minus 1s or e raised to minus s. When we put the initial values in this problem, y of 0 and y dash of 0 are 0. So this term goes to 0, this term goes to 0, and again y of 0 goes to 0. So we have only y bar of s term. I collect it together, y bar of s into, here I have s square, here I have plus 3s, here I have plus 2. So y bar of s into s square plus 3s plus 2 is equal to e raised to minus s. Next step is solve for y bar of s. I keep this y bar of s in LHS and bring this term into the right side. So y bar of s equal to e raised to minus s by s square plus 3s plus 2. Now we apply L inverse on both sides to get solution of this y bar of s. So I express this 1 by s plus 1 into s plus 2 in partial fraction or simple fraction form, then apply L inverse. That is a technique. So apply L inverse on both sides. We get L inverse of y bar of s equal to L inverse of this fraction into u of t minus 1. Because in the previous session we have learned if there is an exponential function in f bar of s term, there is a u of t minus a. Here e raised to minus s, so e raised to minus 1s. So when we take L inverse, there is u of t minus 1. That is why this u of t minus 1. Then we take inverse of this portion, L inverse of 1 by s plus 1 into s plus 2. Then we replace t by t minus 1. I split into two fraction, 1 divided by minus 1 divided by difference. The difference of the factors is minus 1. So minus 1 by minus 1 is 1. Then 1 by first factor minus 1 by second factor. Without using partial fraction, I do like this. Now L inverse of 1 by s plus 1 is e raised to minus t. L inverse of 1 by s plus 2 is e raised to minus 2t. We have that result. 1 by s plus 1. L inverse is e raised to minus t. 1 by s plus 2. L inverse is e raised to minus 2t. Then replace that t by t minus 1. So we got e raised to minus of t minus 1 minus e raised to minus of t. Instead of 2 into t, instead of t I put t minus 1. So this is the result. I can rewrite this in the form of multiple valued function, because this u of t minus 1 depends on this t equal to 1. So I split it into two sub intervals, those values less than 1 and those values greater than 1. When t is less than 1, this is negative. So u of t negative is 0. U of negative value 0. So 0 into this term 0. When t is greater than 1, t minus 1 is positive. U of positive value is 1. So 1 into this expression. That's all. We can finish up to this step, no problem. This is the final simplification step. Instead of L inverse of y bar of s, I write y of t, and I eliminate the u of t minus 1 from the scene by splitting this function into two parts. That's all. The next problem, we are going to see solution of the same ODE. Left side is same, but the right side is combination of unit step function. Steps are same. Apply Laplace transform on both sides, substitute the initial values, then solve for y bar of s, and finally find L inverse. That's all. Then we rewrite this function y double dash plus 3y dash plus 2y into is equal to u of t minus 1 and u of t minus 2. The first step is apply Laplace transform on both sides. Laplace transform y double dash is s square into y bar of s minus, you decrease the power of s by square by 1, so s raised to 1 into y of 0 minus, again decrease the power of s by 1, s raised to 0, that is 1 into y of 0, plus 3 into s into y bar of s minus y of 0, plus Laplace transform y to y, that is 2 into y bar of s. Then Laplace transform of u of t minus 1 is e raised to minus 1 into s, that is e raised to minus s by s, minus this minus Laplace transform of u of t minus 2, that is e raised to minus 2s by s. When I put the initial values in the left side, this s into y of 0 goes to 0 because y of 0 is 0. Y dash of 0 goes to 0, y of 0 goes to 0. So we can collect all the terms of y bar of s. Y bar of s into, you have s square from here, 3s from here, plus 2 from here. So s square plus 3s plus 2 into y bar of s equal to e raised to minus s by s minus e raised to minus 2s by s. Then I solve for y bar of s. That means I keep this y bar of s left side and bring this s square plus 3s plus 2 on the right side. So this s square plus 3s plus 2 come to the denominator of each term. So y bar of s equal to e raised to minus s by s into s square plus 3s plus 2 minus e raised to minus 2s by s into this factor s square plus 3s plus 2. Then I can factorize this s square plus 3s plus 2 as s plus 1 into s plus 2. Here also I can write 1 by s into s plus 1 into s plus 2 into e raised to minus s minus 1 by s into s plus 1 into s plus 2 into this e raised to minus 2s. Next step is apply L inverse on both sides. Here note that here the fractional part is same. Here there is a negative, that is only difference. So we take L inverse of this part and substitute here. That's all. Apply L inverse on both sides of this expression, we get L inverse of y bar of s equal to L inverse of first factor minus L inverse of second factor. See here e raised to minus s, and so when we take L inverse there is a u of t minus 1. U of t minus 1. Then we take L inverse of this expression and replace t by t minus 1. That is a notation. Here also we do that. But here e raised to minus 2s, so the term is u of t minus 2, and so we have to replace t in terms of t minus 2. Then we take inverse Laplace transform of this one using partial fraction, then substitute here. So using partial fraction method, 1 by s into s plus 1 into s plus 2 can be written like this: a by s plus b by s plus 1 plus c by s plus 2. Cross multiplication, I got 1 is equal to a into s plus 1 into s plus 2 plus b into s into s plus 2 plus c into s into s plus 1. Then by elimination I can find a, b and c. When we put s equal to 0, this c term and b term get cancelled because s equal to 0 here. Then a into 2 is equal to 1, or 2a is equal to 1 implies a equal to 1 by 2. Similarly, when I put s is equal to minus 1, this term and this term goes to 0. So I got b is equal to minus 1. Similarly, when I put s is equal to minus 2 in that expression, put s is equal to minus 2, when put s is equal to minus 2, what happened? This term, a term goes to 0 and b term goes to 0, only term is z. So minus 2 into minus 2 plus 1. So minus c is equal to 1. So we got z is equal to minus 1. We substitute these values, c is equal to minus half here. It's not half, minus half. When I put all these values, I got expression like this. C is equal to 1 by 2, not minus half, 1 by 2. Therefore 1 by s into s plus 1 into s plus 2 is equal to a is 1 by 2, 1 by 2 into 1 by s plus b by s plus 1, b is minus 1, so minus 1 by s plus 1 plus this is plus 1 by 2 into 1 by s plus 2. Now take L inverse on both sides. So L inverse of 1 by s into s plus 1 into s plus 2 equal to 1 by 2 into L inverse of 1 by s equal to 1 minus here L inverse of 1 by s plus 1 is equal to e raised to minus t, plus this is actually plus 1 by 2 into e raised to minus 2t. 1 by 2 is here. L inverse of 1 by s plus 2 is e raised to minus 2t. Now the rest is substitute these values. L inverse of y bar of s equal to, here we u of t minus 1. So we have to replace this expression by t minus 1 in the place of t. I put that. And also minus 1 by 2 minus e raised to minus t plus 1 by 2 into e raised to minus 2t. Here we have u of t minus 2, and so we have to replace t by t minus 2. So here instead of t you have to put t minus 2. Here also we do that. That is next step. Using this inverses in y of t, instead of t I put t minus 1 here. Instead of t I put t minus 2 here. Then I split this function into 3 definitions, because u of t minus 1 and u of t minus 2 are here. T minus 1. This u of t minus 1 is depending on the value of t. It gives 1 when t is greater than 1 and 0 when t less than 1. So I choose when 0 less than t less than 1, what happened? This where t is less than 1, that means t minus 1 is negative. So it goes to 0. 0 into this part 0. Again minus. Along with this term we have u of t minus 2 here. It is missing here, u of t minus 2. When t is less than 1, u of t minus 2 is 0. So this term is also goes to 0. So 0 plus 0, 0. Again 1 less than t less than 2. In this interval 1 less than t less than 2, t minus 1 is positive because t is greater than 1. 1 less than t, that means t is greater than 1. So t minus 1 is positive. So we got 1 for u of t minus 1. 1 into this expression, that expression gives. But in that case t is less than 2. T is less than 2 means u of t minus 2 is negative. T is less than 2. So a number less than 2 come here. So negative value. So u of negative value is 0. 0 into this expression 0. That is why we got only the first term. Now come to the last. That is t is greater than or equal to 2. When t is greater than or equal to 2, t minus 1 positive. So u of t minus 1 is 1. So we got this expression. And also t is greater than 2 means this t minus 2 is also positive. So u of positive value gives 1. So we got this term also. That means both the terms will come into role. First term and second term. When we add these two terms, what happened? This is plus 1 by 2. Here I have minus 1 by 2. It sum to 0. Then e raised to minus of t minus 1 plus 1 by 2 e raised to minus of t minus 2 into t minus 1. Here minus is common. Minus into minus plus. Plus e raised to minus of t minus 2 minus half into e raised to minus of 2 into t minus 2. That's all. When t greater than or equal to 2. Up to this term is enough. We can simplify this by eliminating u of t minus 1 by splitting this interval 0 to infinity in this way, 0 to 1, 1 to 2 and greater than or equal to 2. That's all. In this way we can solve differential equation involving unit step function and also Dirac delta function. So as a whole we have finished up to Laplace transform of Heaviside unit step function, second shifting theorem, Laplace transform of Dirac delta function, inverse of function involving e raised to minus as, solution of ODE involving Heaviside unit step function or Dirac delta function. This is all about this session. So by this we ended up the Laplace transform of unit step function and Heaviside function, and also this is end of the Laplace transform and its application. Okay, thank you very much.